So hello, this is a sequence of Karels, just that for me it's the family name. I'm actually not the first author. The first author is Moritz Borisa, together with Markus Hollers and Johannes Tepka and Norbert Pfeiffer. These are the co-authors from the Department of Geodesy and Geoinformation at TU Wien in Vienna, Austria, and further co-authors are D1, who is now with Aalto University in Finland, and Gerhard Bonner from the company of ULS-systems, also in Austria. I will also talk about UAV-LiDAR and the impact of the acquisition characteristics on the quality of derived forest metrics. So we use the study area with consisting of a forest plot of about 20 meters radius, located at Aubergwarte in Austria. It's a coniferous forest. You see here the 67 reference trees with in situ measurements with home stations and calipers overlaid over the canopy height model. On the right you see the distribution of tree heads. So these reference trees, their heights range from about 5 to almost 40 meters, and the distribution of DBHs ranging from below 10 centimeters up to 70 centimeters. These are just impressions, so it's a coniferous forest, rather open managed. As scanners, we used two of them, both manufactured by Riegl. One is the Minibox, downward looking, and the other one is also the VUX-1, like the one used by Karel before. So for those who don't know yet, the Minibox is a polymer scanner, providing us with a typical circular scan pattern depicted here, having an off-nadir angle of 23 degrees and a rather large footprint, which is even rectangular with 16 by 5 centimeters at a distance of 100 meters, a ranging accuracy of 50 millimeters, and a pulse repetition frequency of 100 Hz. By contrast, the other scanner we used, both on board of a helicopter, the VUX-1 is a rather conventional scanner with a linear scan pattern, square footprint, which is much smaller with 5 by 5 centimeters, better ranging accuracy, and a much higher pulse repetition frequency. So with these two scanners, we surveyed our forest plot. You can see the trajectories here. On the left, the one for the Minibox, on the right for the VUX-1. And the forest plot is depicted with these little green points, which is just very small for the VUX-1 dataset. And with the Minibox, we actually captured 3 different datasets, 2 different flight heights, either 65 or 75 meters above ground, and along the edges of 4 pentagrams, which were either big or small. With the VUX-1, we captured just one dataset, depicted here with this, including the cross strips in blue and red. But we also evaluated just a subset of this dataset, which we call the parallel subset, shown in red here. So the point densities we achieved with these 2 scanners and the different datasets, they vary greatly between scanners. For the Minibox, we have 4,000 to 5,000 points per square meter, including all echoes. Well, for the VUX-1, we have either 1,000 or 1,500 points per square meter. So, for evaluation, our workflow consists basically of 2 steps. First, the detection of potential stamp positions. We've already heard that before, but we use a different approach here. Quite a simple one, and then the stamp modeling. For the detection of potential stamps, we first normalize point cloud heights with reference to the DTM, and we evaluate only a slice of a certain vertical extent. Well, then expect potential standpoints, find the actual stand positions, approximate them and use them as input for the actual stand modeling, resulting in DBH and point cloud of standpoints. So for the stand detection, we first normalize the heights, and then we extract a slice of 0.4 to 3 meters above ground points. And then we notice that stand points are mostly represented by last echoes, so we reduce this point cloud to last echoes only. You see the last echoes here in blue, while the other echoes are shown in orange. So using this slice, we now seek for potential stand points. For this, we didn't use a voxel-based approach like we've seen before, but it's directly based on point cloud. We compute certain attributes for each point of this slice of last echoes, and we do this, so we assign 4 attributes to each point, and these 4 attributes form 2 groups, and each group is just based on a certain neighborhood of this point. The neighborhood is always defined by a vertical cylinder with a radius of 20 centimeters, and we either consider only the lower points of the slice from 0.4 to 2 meters, or the slice above until 3 meters. And we consider, finally we investigate all these 4 attributes, including the point counts in the respective slices, and we consider as potential standpoints only those that have an average 2D point distance in both slices below 0.1 meters, below 0.1 meters, and of course, as a precondition, we need a point count above 1 to compute these distances. Yeah, so now that we have potential standpoints, we need to find potential stand positions. We don't do this directly with, or as we've seen, there are different approaches to initialize a nonlinear adjustment of a cylinder, for example. We don't do this using RANSAC, but we use the following approach. First of all, we want to get rid of branches, points on branches, and for that we compute the range of heights for points within the cylinder, in vertical cylinder neighborhood with a radius of ½ meter, and this range must be at least 1.5 meters. So this ensures that there is that we are having a point within a certain vertically oriented neighborhood. Second, we want to find local maxima in the distribution of 2D point densities. For that, we compute a 2D raster of size 0.1 by 0.1 meters, and we require potential local maxima to have at least 5 points, and to be local maxima within a grid of ½ meter by ½ meter around this grid cell. So finally, this local maxima, the center of these cells, will be considered as potential stand positions, used to initialize the actual stem reconstruction. So the input to this is again the point cloud slice from 0.4 to 3 meters above ground, and the approximate stem positions we've computed before. For the stem modeling, we estimate either cylinders or cones. There is badly visible, unfortunately. But you can see here such a representation of one stem in the point cloud slice here in the top view, which is hardly visible, and here on the side view. So now to the results. First concerning stem detection. On the left we have the results for the 3 Minibox datasets, and the right for the VUX-1 dataset. The results are grouped into 6 results, or groups of 6 results. On the very left we have, for example, the miniVUX dataset flown 75 meters above ground along the small pentagrams. On the right for the VUX-1, we have on the left the full dataset, and on the right only the parallel subset. So, and within each group, we have on the one hand results for fitting cone models in bluish colors, and for fitting cylinder models in reddish colors. Each result then is also based on a certain point cloud slice with a certain vertical extent. On the left, we have the largest extent of 0.4 to 2.2 meters above ground. On the right, we have the smallest or thinnest slice with just 1 meter extent. All of those extents are symmetrical about the DBH of 1.3 meters. So what we can see from these plots is that overall, stem detection worked best for us for the miniVUX dataset, less well for the VUX-1. We can also see that there is no clear difference for whether one estimates a cone model or a cylinder model, but there is quite a clear trend that stem detection works better for thicker point slices. So these left bars here, for these ones, the detection rate is higher. Detection overall goes up to 91%. Karel just before reported detection rates of up to 100%. We haven't achieved that, but these data sets, they are both of much lower density. Now, concerning results about DBH estimation and its error, plots are quite similar to the slide before. Again, groups for the datasets, and then cone fitting and cylinder fitting, and different vertical extents of the point cloud slices. However, when it comes to estimating the DBH, results are much better for the VUX-1 dataset, especially when using the full dataset. So here, the DBH error goes down to below 1 millimeter, which is surely sufficient. Also, the trend is different here. So DBH error is smaller for thinner point cloud slices, which seems very plausible indeed. Results are quite much worse for when using only the parallel subset, almost on a level with the results from the Minibox. So now, concerning the point height distributions of these two data sets, on the top we have histograms of vertical distributions of all returns for the full height range from up to 40 meters above ground. In red we have the distributions for the miniVUX dataset, in black the ones for the VUX-1 dataset, and as we can see here in the plot of total counts and all returns, we have far more returns with the miniVUX. And also relatively, the relative distributions along the height axis. The miniVUX points, they reach further below relatively than the VUX-1 data. Now if we focus on the lower heights up to 5 meters above ground, and only on the last bit turns, which we used for stand detection and modeling. In absolute numbers, there is more, a denser sample of the Minibox datasets, and relatively, well, there are no clear changes in the distribution, very close to the ground. Now, how about visually assessing or possible reasons for the much smaller DBH estimation errors with the VUX-1? Here we see a top view of a small slice of 0.4 to 2.2 meters above ground for the Minibox on the left and the VUX-1 dataset on the right. And well, just visually one can see how much less noise there is in the VUX-1 data. So even though there is, even though the point density is much higher for the Minibox dataset, DBH errors are still much lower for the less dense sample of the VUX-1. So as an outlook, we've so far used a really simple approach for the whole workflow. There are several ways how to improve on that. For example, we actually have a ready-made workflow for leaf and wood separation introduced by D1. And then another improvement would be to segment the point cloud into stands for improved stand position approximation. So the workflow presented here was implemented in our comprise software. If you're interested, you can download the test work. Thanks for your attention.